Okay, so welcome everyone to this IOA Distinguished Lecture. Gives me great pleasure to welcome Professor Eugene Chiang from Berkeley to give this distinguished lecture. Eugene did his PhD in Caltech, which he finished in 2000, before moving to the Institute of Advanced Studies in Princeton for a Hubble Fellowship. And then shortly afterwards, he moved to Berkeley with a faculty position where he has been ever since. He's risen to the dizzying heights of being the chair of the department from 2015 to 2018, which I know comes with a lot of rewards and challenges. But he's been a great leader of the department through that time. Eugene's research covers a broad range of topics within theoretical astrophysics. Most of these within extrasolar planets and circumstellar disks, but a broad range within that. He's developed the leading models for interpretation of protoplanetary disk SEDs. You may remember from your thesis, that's still very widely used. But it goes across the range from models of evaporation of planet atmospheres, the origin of superpuff planets, disintegrating planets, structures within protoplanetary disks, the origin of super-Earths, the structure in the Kuiper belt, the structure in extrasolar Kuiper belts. And there's a truly impressive range of topics that he has worked on and led the theoretical development thereof. And fortunately for you, he is also an excellent speaker. No
pressure.
No pressure, Eugene. But I think this talk has the enigmatic title of "Some Disassembly Required," which will bring together, I think, many of those topics. So I'll hand over to you.
Thanks very much, Mark. Thanks very much for the overly kind introduction. Referring to my time as chair, it's not dizzying heights, it's dizzying depths. It's definitely dizzying, that's for sure. Thank you very much for inviting me here. I've had a lovely time in Cambridge, thanks to all of your hospitality. My talk today is on planet formation, or really the flip side of formation, planet destruction. I think it's a fine line between creation and catastrophe, but many properties, I think, of planetary systems cannot be understood without also accounting for what would we call it, random acts of violence. So we'll review some of these today safely, mostly involving catastrophic collisions, but also involving death by vaporization. So let's start with a plot that shows a bird's eye view of everything under the extrasolar sun. This first part of my talk is going to focus on the most common demographic, super-Earths and sub-Neptunes. These are bodies up to about 20 Earth masses, orbiting inside of an AU, sometimes often well inside. They orbit around more than half of the stars in our universe. In our solar system, we have our own set of super-Earths. It's just that they're not so super. We call them Venus and Earth. I prefer to think of them as just a low-mass, slightly further out extension of this population. What's important, I think, is to keep in mind that solar system terrestrials, extrasolar super-Earths, and sub-Neptunes, they all share a common lineage. They're all predominantly, basically, balls of rock. So here's where they sit in radius mass space. Many of them are consistent with bare silicate spheres with some admixture of metal, Earth-like composition. The larger ones that range up to about 4 Earth radii, to explain their puffiness, you can overlay that rock core with a hydrogen-helium envelope. Okay? You don't need much mass in hydrogen, maybe just a few percent by weight. You can read off the gas mass fraction here, so maybe a few percent by weight in hydrogen, enough to inflate the radius by factors of several. We call them hydrogen-helium atmospheres, but we recognize that they must be highly enriched in metals. Not enough, I think, to change the mean molecular weight by very much, but definitely enough to produce all the clouds and the hazes and the rich molecules that have been seen in their atmospheres. Now, I understand there is an alternative interpretation, right, for these sub-Neptunes. Instead of being balls of rock overlaid with hydrogen, they could be worlds more similar to Neptune and Uranus, so balls of water worlds, made predominantly of water ice. Possible, yes, just given a radius and a mass. I think, for the most part, unlikely. There will be exceptions, okay? But for the most part, the majority of systems, I think, are really gas dwarfs, because if they're gas dwarfs, it's easy to understand why sub-Neptunes and super-Earths have this bimodal radius distribution and why they separate out in this space. This is basically stellar intensity. So super-Earths are systematically closer in than sub-Neptunes, which makes sense if their atmospheres are made of hydrogen, because that hydrogen can be heated by X-ray, UV radiation from the star, heated to the point of escape. If you lay bare that rock, sub-Neptunes become super-Earths. Okay? Now, to the extent that all of these objects, if you lay them bare, strip them bare, they're all balls of rock. They all form, we think, the same way, from collisions. Small rocks banging together to become ever larger bodies. For the Earth at 1 AU, we think this process unfolded over the course of about 100 million years. The last giant impact that formed the moon, we can date to something like 50 million years after time zero, where time zero is the first event that we can trace, the condensation of the first solids, calcium aluminum inclusions in primitive meteorites. We'll come back to that later. Sub-Neptune, super-Earths, we think also formed from the ground up, bottom up, small rocks banging together become larger rocks, but we think that happened just over a faster time scale. Many reasons for that. Maybe a more compelling one to me is that because these sub-Neptunes have hydrogen atmospheres, envelopes, the cores had to have formed while the primordial gas disk was still around, right? The original protoplanetary disk. And that disk is only around for something like 1 million years or so. Okay, so to accrete these envelopes, they had to have been present while the gas disk was still present to some degree. And we'll quantify degree right now. Here's a calculation of the gas mass fraction, okay, versus time. I place a core, 7 Earth masses at 0.1 AU in a sea of gas, and I just watch and calculate how that core accretes gas, okay? These different colored curves correspond to different assumptions about the ambient gas density. All the way up to the maximum gas density, what I call a high mass disk, that's basically a solar composition reconstruction of what the primordial disk, extrasolar disk may have looked like. For those of you who know, this is completely analogous to the minimum mass solar nebula just applied to extrasolar systems. So it's a solar composition disk, but we can also consider disks that are depleted in hydrogen, and there's these lower curves. If there's too much hydrogen in the disk, things are actually bad. You explode. You accrete too much gas, okay? It undergoes what's called runaway. This whole process of accreting gas, it's all about thermodynamics, at least in the initial stages, right? So you have a core, rocky core, in a sea of gas. It binds to itself all the gas within its gravitational sphere of influence. For these close-in objects, that's going to be the Hill sphere, aka the Roche lobe. And if you want to grow that atmosphere, you just wait. You wait for the gas to cool radiatively. So in cooling, it'll contract a little bit, underfill the Roche lobe, and then allow fresh gas to seep in. Okay, so it's accretion by cooling. That cooling, there's a catastrophic limit where the cooling time decreases with increasing gas mass when you account for the envelope's self-gravity. Okay, this is kind of gravothermal catastrophe, which we call runaway. Great for forming gas giants, terrible for forming sub-Neptunes, right? You want to preserve, you want to create just a few percent by weight atmosphere. So you need to deplete the gas disk. Good news is that a whole range of depletion factors can be accommodated, okay? This varies by orders of magnitude in the gas density relative to the solar composition, but all roads seem to lead, more or less, within a factor of several, to these few percent by weight atmospheres. And many ways to understand this. Maybe the shortest way to say it is that percent by weight atmospheres are commonplace in the universe because percent by weight atmospheres have cooling times that are on the order of the lifetimes of protoplanetary disks, okay, which is on the order of 1 million years. You only have that much time to accrete, and so you cool in that time and you pick up a few percent by weight. Good. Now, where you find one sub-Neptune, you are very likely to find others orbiting the same star. They're social. They're born into big families. Their orbits today are more or less random. Okay? If I plot the period ratio between adjacent pairs, that's this histogram here. That period ratio, P2 over P1, can take really any value. There's a whole continuum of values. It could take any value. Except you'll notice that there are these exceptions where there are excess populations near these mean motion resonances, 3 to 2 and the 2 to 1. 3 to 2, of course, is the resonance where the outer planet makes 2 orbits for every 3 that the inner one makes. So you find these excess populations, but they're the exception, right? Not the rule. Just a few percent of pairs are in near these resonances. Even more rare are long chains. Like Kepler-11 was the first announced, I think. 6 planets exhibiting this sequence of harmonics. Alex Parker has matched the orbital frequency to the acoustic frequency, and he hits a key on the piano every time there's a transit, so that you can literally hear the music of the spheres. That's nice, but I will tell you that I love, or at least I used to love, ignoring systems like Kepler-11. The level of complication here is too much for me. N is too large. N of 6, I sort of crap out at n equals 3. So, have fun with that, all you dynamicists out there. I thought I also had good reason to regard long chains like Kepler-11 as just a curiosity, not a common outcome of planet formation. Just look at the statistics, right? They're rare. Most systems are not like that. Boy, was I wrong about that. And I was corrected on this point by Fei Dai. Many of you know Fei. You worked with Fei. He was a Cambridge alum, undergraduate here. He says hi. And I've been working with Fei. Fei, okay, has a time machine. Time machine is called TESS. People who work in planet formation, we die for time machines, right? We want to go back to figure out what happened. TESS is a time machine because it's an all-sky survey. So it can find sub-Neptunes, okay, in clusters and stellar associations. And those are young, okay? Not like the Kepler field, which was all old stars, all main sequence stars, all stars older than a few billion years. So if you look at the TESS data now, which is just coming out, right? Here are the systems between 0.1 and 1 gigayears. This is plotted on the y-axis. And here he's plotting where the planets are in period space. And many of them are near resonances. He's labeling them. Okay, he colors the ones. He draws a line in the sand. So every time the period ratio is within 2%, a few percent, of perfect commensurability, he colors it in. The colored systems are about 7 out of 15, much more than the few percent, right, that characterize the older systems. If you look at the even younger set, here between 0.01 gigayears and 0.1 gigayears, they're nearly all in resonance. 6 out of 7 of the systems exhibit near perfect commensurability. So these data are pointing to all sub-Neptunes having formed in resonant chains. but those chains having broken over time. So some disassembly is definitely required. These data are pointing to sub-Neptunes migrating within disks. That residual gas disk exerts torques on the planets, causing them to spiral in. It's just a form of dynamical friction, okay? The same dynamical friction that causes black holes to center to the spirals of galaxies. You get a rearrangement of the orbits, generally a shrinkage of the orbits inwards. And you need that movement, okay, of the planets in order for the planets to lock into resonance. They're not just born into these magic configurations. They were born, say, randomly, and then they lock into resonance. And here's a little illustration of that. So plotting the two planets here in orbital period. Okay, they're not in resonance. The dashed line marks the location of the resonance. I'm just going to move these planets by hand to simulate the migration through the disk, and you watch as the planets catch each other into 3-2 resonance. And the resonance amplifies the eccentricity in continued migration. More realistically, the eccentricities are kept low, much lower than this, we think, because the same dynamical friction that changes semi-major axes also damps eccentricities. It circularizes the orbits. So there's a balance between the resonant amplification and the damping of eccentricity from the disk, which keeps the eccentricities low. Okay, pretty low, really low, less than 1%. Okay. We think now, this is a picture that is really just emerging with the test data, that all sub-Neptunes form in long chains. They migrated to lock themselves into resonance. Over time, those resonances break apart. We don't know if there's some universal or specific mechanism that causes the instability. It could just be sort of generic chaos associated with large N systems. I like to think of it as, if you have a planetary system, when it's born in the disk, that disk is a stabilizing influence, right, on it. It damps the eccentricities and keeps everything stable. When the gas disk dissipates, then the planets are free to jostle each other around, and the eccentricities random walk to the point where they merge. 6 has become 4 planets. When the orbits cross, they merge. They're too close to their host stars to eject each other. Sometimes ejection happens, but for the most part it doesn't. When the orbits cross, the planets cannibalize each other in these catastrophic mergers. So when I look at the distribution today of period ratios, right, these little fingers pointing out associated with these resonances, I see them as the ruins, right, the remnants of once great towers, where all the planets were assembled into these resonant configurations, which over time have broken apart into fused in period space to form this continuum with just some ruins left over, the remnant peaks. Okay, so that's the going into. So there's a lot more I can say about this. So I don't have the time, but I'd like to switch gears now and talk about catastrophes or collisions in another setting, the setting of debris disks. I can talk more about these resonances later, if you'd like. The going interpretation, right, for some debris disks, I think this audience needs no reminding, right, that some debris disks, the going interpretation is to explain that emission, it came from, perhaps, the catastrophic collision of 2 planet-scale objects. The evidence for this takes the form of high-temperature minerals like obsidian, inferred from spectroscopy, CO gas, perhaps stripped from the atmosphere of a planet as it underwent a giant impact. These data speak to collisions on sort of the inner regions of planetary systems, inside of several AU. What I'm going to focus on is the evidence for collisions on larger scales, on Kuiper belt scales. I wasn't looking for collisions, okay, per se, but it turned out, at least for me, to be the only explanation that made some sense to explain otherwise very strange images. And by strange images, I mean images that look like these. This collection of debris disks, which don't look like, right, your usual ring or projected circle or even an ellipse, right? These look weird. Instead of rings, you get wings, ansi, that are swept back. In this case, there seems to be a secondary ring, or wing, that runs parallel to the first. In addition to wing disks, you also have lopsided ones, which are short on one end, long on the other. Sometimes those extensions are forked. They split into two, either on the long end or on the short end. These are all non-axisymmetric shapes. What's the most non-axisymmetric shape you can think of? The most non-axisymmetric shape that I can think of is a delta function, displaced from the origin. Where am I going to get a delta function? Well, I can get a delta function from a collision. A planet that underwent a disruption, okay, collision, smashed into bits. Those bits, the largest fragments, will differentially rotate into a torus, which is pinched. And here again, I'm just summarizing work that was done here at Cambridge. There's a pinch point because what goes around comes around, right? At the collision point, the fragments are sprayed out with some dispersion of ejective velocities, but they all have to come back to the same point. Not all at the same time, but back to the same point because orbits close, barring, right, differential precession and smearing out of this collision point. This point to which, all the particles come back repeatedly over and over again, it's at this point where densities are highest, particle densities are highest, where relative velocities are highest, and therefore collision rates are highest, right? I think of it as the gift that keeps on giving. This is a delta function source of dust. It's like a fountain of dust that just keeps pouring out, continued bits and debris. This is the immediate aftermath of the collision. We're going to assume that at this singularity, there is a delta function source of dust. That dust is blown out by radiation, pressure from the star, also wind pressure if the star is active and blows a wind, into this pattern. It's blown out onto highly elliptical orbits, okay, which trace out this pattern. I call these grains the halo grains. They're blown out into highly extended orbits. They're still bound, barely. Okay, so they build up a steady state population, or they try to approach steady state. There's a lot of grains in the halo. There's a lot of grains in the halo because they're blown out onto such highly eccentric orbits. They spend a long time lingering at their apoapses, right? It's mostly empty space out there. They're protected from collisions. They don't collide very much out there, right? And so the closer you are to the blowout size, the more elliptical your orbit is. The more elliptical your orbit is, the longer is your collisional lifetime, right? The more immune you are to collisions. And therefore, the more your population can build up as the grains continue to grind away. So there's a strong deviation from this classic Donyan-Yi power law. And this has all kinds of observable consequences. You can use it to explain how the surface brightnesses of debris disks decays with distance. This is measured. You can reproduce the images in many cases. There's so many grains, okay, near the blowout size. These are all micron-sized grains that they can actually dominate the millimeter wave emission and explain the millimeter wave halos that are seen in debris disks around from ALMA, right? So the usual rule of thumb that when you observe at wavelength lambda, that you're sensitive predominantly to grain sizes of order lambda or lambda over 2 pi, that rule of thumb does not apply for this system, for this situation, because there's such a strong deviation from this power law size distribution. Okay, the millimeter wave emission is dominated by micron-sized grains. The other observational consequence is that we can try to use it to explain these winged disks and lopsided ones as well. The pattern is traced out like this. It kind of looks a little funny, like a fish. There's this limiting parabola, right? Barely bound, eccentricity 1 minus epsilon grains. But then there's also these 2 jets that spread out the backside. The jets are just a consequence, qualitatively, of two competing effects. On the one hand, the grains are trying to concentrate at peri, because that's where the collision point is. But at the same time, the grains are in highly elliptical orbits, so they linger at apo, and so there's a traffic jam of grains. There's a buildup just from continuity. The linear density of grains is higher at apo. So on one hand, you want to concentrate at peri. On the other hand, you want to concentrate at apo. The net is that you concentrate at neither. You concentrate at an intermediate angle between peri and apo, and that angle is reflection symmetric about the epsidal line. Okay, so that gives rise to these overdensities along these two rays. I'd like to emphasize that we tried to get this, not with the collision, but with just an eccentric disk, right? An apse-aligned eccentric debris disk. That you can get that either from gravitational forcing from a planet. You can try to use self-gravity to create these m=1 modes. They won't give you the jets, because the jets occur because we have a delta function-like source right there. For these other modes, m=1 modes, eccentric disks, forced by a planet, the source region for the dust is too smeared out, right? It's always subtends an angle of order unity. It's too broad. And so you take this pattern and just you smear it out, and you don't get this structure. Okay. You really do need something like a delta function, a source region that subtends an angle much less than order unity. Okay. The jets are interesting because if you look at them the right way, and here, this is face-on view. I'm going to tilt it over now so that you're looking at it edge-on. Now the entire wash of dust is like pointing towards you. The primary parabola, right, projects into the primary wing, and then the two jets project into the secondary wing. When you turn it around in azimuth, then you can get a lopsided disk, and that's fairly straightforward. So this is what we think is going on for 32297, right? I'm not sure if the lighting is doing the image justice, but there is a secondary wing up here, right? And we try to reproduce it using this collision point model. How much dust are we talking about? Maybe a Pluto's worth, okay? You can't have too much. The thing that got destroyed couldn't have been that massive because you need the fragments to fly off the surface. So collision velocities are limited to about 1 kilometer per second out there on Kuiper belt-like distances, which limits the ejective velocities to about that velocity, which means that the surface escape velocity can't be it has to be less than this, which causes you infer a mass for the progenitor about the size of Pluto. And when you do the radiative transfer reproductions of this disk, you wind up with about a Pluto's worth of mass. So a Pluto, a dwarf planet, got smashed to smithereens. Here's the blue needle. It's actually two needles, one that points this way, another one that points this way. We think that's two catastrophic collisions that happened. Encouragingly, if you look at ALMA, there are actually two belts, one nestled inside the other. These are limb-brightened rings. A way to test this idea is to, I think one way to test it is with spectroscopy, because the minerals that you get from these high-velocity collisions, from melting collisions, will be different from the collisions that happened sort of more gently in other systems. A last example of collision point dynamics, AU-MIC, everyone's favorite M-dwarf. By the way, AU-MIC is one of those test sources, I don't know if you noticed, it has a chain of 3 resonant planets around them, sub-Neptunes found by TESS. AU-MIC is a debris disk which is also lopsided. It has waves on one side and not so much on the other. VLT has resolved those waves into clumps. And over time, these clumps move across the sky. There's a proper motion. It's a pretty fast clip, several kilometers per second, okay, on escape trajectories, leaving the system, but only on one side. So what's going on? What we think is going on is that there was a collision in the past, the disruption of a body, maybe the size of Varuna or Ceres, a little less than Pluto. It happened here, almost along the line of sight to the star, okay? And there's a stream of dust which traces out this kind of staircase pattern. This is the delta function source, which is spitting out this stream. The stream is on escape trajectories now. They're unbound because the wind from the star blows too hard. AU-MIC, it's an X-ray active M-dwarf. It flares in the X-ray. There's so much pressure, ram pressure, from the X-ray flares. People estimate a force from the wind pressure during a flare, which is some 40 times stronger than the force of gravity from the star. Now, what we assume is that in addition to these sporadic X-ray flares, we assume that there's a long-term trend in the stellar activity, like the solar cycle, okay? So every 10 years, the wind gusts so that this force ratio is high. And in the low state, it's maybe an order of magnitude lower. This is the model that we use to generate the staircase pattern, because when you fold in this cyclical stellar wind, every radial zag corresponds to when the wind blows really hard. And every horizontal zig is when the wind is in the low state, and then it's just carried by disk rotation from the west to the east. Now you're looking at it this way, and so every one of these radial stretches gives you a large column density, a large line of sight column density, which makes for a bright clump. So what you see in projection are these clumps moving through space, emanating from that collision point, which does not move in inertial space, right? It's fixed to wherever the collision happened. It must be an incredible light show. If you were a planet traveling through this stream, it must completely blow the Leonids out of the water. The velocities from these grains are so large, a few kilometers per second, that they must be highly destructive, right? One collision creating hundreds of secondary particles, showers. We call this a dust avalanche. There's an exponential amplification in the dust flux along one of these radial paths, right? It's just like any other exponential amplification, like in a laser. There it's the amplification of photons, right? Photon number, photon flux. Here it's dust flux. And when you account for that exponential amplification, you can reproduce the cloud masses that are inferred from the HST photometry. So here's a summary of this portion of the talk. And I've assembled here all the disks that I thought were weird in their asymmetries as seen in scattered light. Beta Pic is here. You'll notice here possible explanations. Giant impacts, not always the right explanation, I think, but one can make the case in several of them. Here, Yinwo has done great work in establishing that this is maybe the right explanation for Beta Pic. It's just a few systems, right? But even if it's just a few percent of disks, where you see the visible scars of these catastrophes, because the window of observability for this impact is so short. I mean, it's estimated to be maybe tens of thousands, maybe 100,000 years for this torus to sort of grind itself away and merge with the background. Because the window of observability is so short, for every one of these collisions that you sort of catch in the immediate aftermath, it must imply a huge reservoir of bodies, okay, uncollided progenitors. And just to give you a sense of scale, here's a standard model for the Kuiper Belt. It predicts size distribution. It predicts something like, this red curve, something like 100 Plutos, right, at 100 AU scales. But if you take the extrasolar data and this giant impact statistics, it's large error bars, but it implies maybe orders of magnitude more bodies, maybe tens of thousands of dwarf planets running around out there at 100 AU. And maybe we'll see some of them with Rubin, all sky survey, right? The synoptic survey, or maybe even with microlensing, we might catch some of the bigger ones around extrasolar systems. Okay. Speaking of rocks falling from the sky, chondritic meteorites also record a history of violence, collisions, high temperature events. It's been a big mystery for as long as people can remember, over 100 years since Sorby discovered them. What melted these little chondrules, right? You take this meteorite, crack it open, and it's just filled with these little BBs. Okay. These sub-millimeter sized spheres, they must have been molten in space so that surface tension pulled them into spheres. And then, just as mysterious, some mechanism must have collected them with incredible efficiency so that their volume filling fraction, it can approach 100%. It's filled with these things, so incredibly efficient collection mechanism. They're the oldest things that we know of. When people talk about the 4.567 billion year age of the solar system, they're referring to these rocks, right? The radioisotope ages for chondrites and for their high temperature counterparts, the CAIs. I have a sample here. People are free to take a look afterwards if you'd like. You can even take it out of the box. You can hold it. I just ask you that when you do hold it, that you handle with care. You know how to handle antiques, right? Like Ming Dynasty vases, okay? Came out of the kiln, okay? You know, thousands of, hundreds of years ago, okay? This thing came out of the kiln 4.56 billion years ago. It hasn't been heated since. Okay, so fragile. A case can be made that at least for a subclass of chondrite, the so-called CBs, that they are melt droplets from a high velocity collision. And there are a couple lines of reasoning for this. We've added to it. Maybe the strongest piece of evidence, I would say, is the chemical composition. They're not like ordinary chondrules. They have a high proportion of metal. I mean, here they are, maybe these silvery things, okay? And the cosmochemists tell me that to reproduce the proportion of iron to iridium to palladium to nickel, that these melt droplets must have condensed from a vapor that was supersolar in metallicity. And by supersolar, if you read the fine print, supersolar is 10 to the 7 times solar metallicity. So take that for supersolar. It's basically a pure metal gas, right? So where are you going to get that, right? Heated to, a fraction of a bar to thousands of Kelvin. You're not going to get that from I don't think you're going to get that from the primordial hydrogen disk, but you can get it from 2 asteroids smashing together and the plume condensing out and producing these melt droplets. So what we've done is we did a little set-off-Taylor calculation. It's set-off-Taylor light because we don't actually resolve the explosion in space, but we do resolve it in time. So we solve for the mean radius and temperature and pressure of this cloud of vapor from the impact as it expands out into the solar nebula, okay? And here are the equations of mass, momentum, and energy that we solve for. Much of the evolution is characterized by the pressure being regulated by the saturation pressure of vapor over rock, right? Because as this cloud is cooling and condensing, the pressure is regulated to be the saturation vapor pressure for much of its evolution. The motivation for this calculation is that we want to reproduce the cooling rates that my meteoriticist colleagues tell me for CB chondrules and other chondrules too, between 100 and 1,000 Kelvin per hour. They were molten, fine, but then they cooled off and became solid at a rate of something like 100 to 1,000 Kelvin per hour. Any faster than that, and they're too glassy. Any slower than that, and they're too crystalline. So you gotta hit it just right. So we can use our calculation to translate this into the scale of the asteroids that must have collided, right? Because if the asteroids were too small, sure, you can get vapor, sure, you can get melt, but the thing will be over in a flash if the colliding bodies are too small. If they're about 10 to 1,000 kilometers in size, then yes, we can reproduce these temperature T dot, the rate of cooling versus temperature, these thermal histories. They have to go through these gray regions, which are the good regions. Notice, right, if it's between 10 and 1,000 kilometers, it can do it. Vacuum cooling is hopeless. It's way too fast. Even cooling along an adiabat is too fast because you're not accounting for all the latent heat, the heating from latent heat due to this ongoing condensation of this condensing cloud. This is, I think, encouraging. 10 to 1,000 kilometers is a typical size of an asteroid. It's where most of the mass is, right, for the asteroid belt. But now your problems really begin, because the sign is wrong. How are you going to put Humpty Dumpty back together again? I wish I knew. The sign is wrong. It's going that way. And we want to bring everything back together again to form the chondritic meteorite. If you can figure this out, let me know. We'll write a paper together. Or you could write a paper yourself. I'm working on several ideas. One of them is that maybe the sign is right. Maybe there's some fallback, okay? If this the fragment of the body that's left over is large enough, it can pull the fragments back, all right, the slower moving ones. The problem there is that I can't have them fall back too fast, right? They have to sort of rain down gently back onto the surface, because if they come down too fast at the full escape velocity of a 1,000-kilometer asteroid, they would shatter. And they're not shattered. They come down, at speeds of, say, less than 30 meters per second. Okay, so it has to rain down gently after being thrown out violently. Shattering is not a problem for the chondral and CAI fragments that have been returned to the Earth from comet Wild 2. Recall there was a Stardust mission which actually picked up grains from this comet and brought them back to Earth. Some of those grains were very surprising. They were high temperature minerals. People call them CAI-like fragments and chondrules, heated to temperatures of a few thousand Kelvin. This was a big surprise because how are you going to get that level of heating from a comet which is cold, presumably came out originated from the Kuiper Belt? I think the most popular ideas are, well, they form close to the sun because that's where it's hot, and then we're thrown out, by orders of magnitude in distance, out to Kuiper Belt-like distances, maybe through a wind or through a disk which had to be strongly radially mixing. I'm not so sure any of that is needed. I think you could explain these fragments as just the collisional fragments of high velocity in situ collisions that happened between dwarf planets in the Kuiper Belt, and these comets picked up all that debris, and that's what we picked up. Okay, so I'll leave that as an idea. And in the remaining time I have, I think I have, maybe 10 minutes or so. Okay, I'll give you one last episode of destruction. It does not involve collisions, but it does involve vaporization. It's ironic. The Kepler space mission, in its 5-year search for strange new worlds, some habitable, hopefully, it's ironic that instead of finding life, it found death, a dying world, we think, in the form of KIC 1255b. KIC stands for Kepler Input Catalog. For many years, this object did not have a proper Kepler designation. It was not recognized as a planet for many years because people didn't know what it was. Okay, now it has a Kepler designation, and I'll tell you why we think that. Its light curve is completely bizarre. It's a K-star, okay, just sitting out there in the galaxy. Every 16 hours, something occults it. Okay, sometimes the transit depth is as deep as 1%. Or so. Yeah, 1%. That means a body, an occulting body the size of Jupiter, okay, crossing the face of this K-star. But other times, 16 hours later, it's unobservable. And then comes back again, and then it disappears again. Most of the time, the transit depths are completely erratic. The period is like clockwork. You can measure it to 6 significant figures. Okay, but the transit depths are anything but. They're completely random. So what's going on? This can't be a hard sphere transit, right? Unless you can think of a way to take Jupiter and make it go poof in 16 hours. We think it's a wind. The wind has to be an erratic wind, a very gusty wind, a wind that must be filled with dust, right? You need dust to give you the continuum opacity to block out the light from the star. A dusty wind emanating from the surface of this object, which at 16 hours is hot enough to vaporize. The dust comes out in the form of a tail, like a comet. We know this because the shape of the transit is fast going in and slow going out. Slow going out because it's dragging the tail across the face of the star. There are several objects like this now. It's not just KIC 1255. Here's another one, Kepler object of interest. Even Beta Pic, right, has, I learned a few years ago, has these shark tooth or shark fin-like patterns in its light curve, its own set of comets flying across the face of its star. Oh, this was an animation which we can play for a little bit just to give you a feeling for it. Okay. The object can't be too big. The thing in the middle, the nucleus, cannot be too large. At a temperature of 2100 degrees Kelvin, the sound speed of rock vapor is just shy of 1 kilometer per second. And in order for the wind to escape the surface, the escape velocity can't be much larger than that, which limits the size of the mass of the object to be about less than the size of the moon. We actually think it's close to this upper limit in order to produce the mass loss rate in dust that is observed. Okay, about 1 Earth mass per gigayear is the m dot. We can only get that if it's close to this upper limit. What we think is going on is an object, it's started off larger than the size of the moon, maybe several times larger, maybe the size of Mercury, or a fraction of that. Well, actually about a Mercury, okay, sitting there in a 16-hour period, sort of just bubbling away over billions of years. Okay? And because the mass loss rate is exponentially sensitive to surface gravity, right, the wind really kicks in when it's been whittled down to about the size of the moon, and now we're just catching it right on the cliff when it falls off this mass over time cliff, and we're catching it in the sort of fireworks phase of its demise. That's the long-term time evolution, we think. What about this crazy chaos? Well, it must be something like the weather, right? So what's the weather like on KIC 1255? Clear skies today on 1255, highs in the high 2100s. It's going to be a real scorcher. Get ready for that thermal evaporative wind that's going to blow so hard and dredge up so much dust that the 16-hour forecast will be for very cloudy skies. So cloudy that the surface will cool, the wind will shut itself off, skies will clear as whatever dust that's in the atmosphere precipitates out or is thrown off to infinity, okay, and the cycle will restart. There's a natural time scale for that cycle, which is very conveniently just the orbital period. And that's because that's how long it takes for the wind to travel from the surface to the edge of the Hill sphere, where Coriolis forces will turn it by an angle of ordered unity out of the line of sight up to the star. Okay? So there's a natural time length scale for the flow, and there's a natural time scale for the flow to refresh itself. And the Hill dynamical time is of order the orbital period. So this is basically the sketch that we have. We can do better. We can try to create a map, a simple map that evolves the wind. Okay, that evolves the system from time I to some time I plus 1, an iterative map. In nonlinear dynamics, people create these maps all the time, right? Maybe the most famous one is the logistic map from biophysics. Famously chaotic, right? It just looks parabolic, but it's a very simple map, and it creates all this crazy patterns. Models population booms and busts. We thought to ourselves, well, surely we could write down a map that might, approach the complexity in KIC 1255. There are 3 ingredients to our map, very simple. The mass loss rate at some time I is exponentially sensitive to the temperature on the ground. That's just Clausius-Clapeyron for the saturation vapor pressure of the vapor over rock at the surface of the planet. The temperature, ground temperature, depends on the optical depth, tau, right, at that same time. And this temperature profile depends depends on the ratio of opacities in this two-stream solution. It depends on the opacity at visible wavelengths, which is the first stream, and then the outgoing stream is the infrared radiation. It depends on the ratio. To the opacity at infrared wavelengths. So when the atmosphere is absorbing more in the visible than in the infrared, you get what we call nuclear winter solutions, where the ground is colder than at altitude. But if gamma is flipped, if gamma is less than 1, it absorbs more strongly in the infrared than it does in the visible, then you get a greenhouse effect where the ground is warmer than at altitude. Okay? So depends on what the atmosphere is made of, which we'll get to. Final ingredient is you need to build some memory into the system. And there's this atmospheric refresh time, right? 16 hours. So the mass loss rate at some time I tells you what the optical depth is 16 hours later. That's the iteration for the map. That's the +1. When you combine these equations, you get a 1D map. It's not the prettiest looking thing, but it is a 1D map. It maps the optical depth, right, from some time I to I+1. It's very simple, actually. If you plot tau I plus 1 versus tau I, this is the map. It's this blue curve. It's exactly what you would expect. If it's clear skies, it's cloudy the next day. If it's cloudy, then it's clear skies the next day. And depending on parameters, you can get all kinds of behavior. If for this a mild nuclear winter gamma, there's one fixed point in the problem, right? And it relaxes to that fixed point. If the nuclear winter gamma is a little stronger, the map steepens, you destabilize that fixed point. It's an unstable fixed point now. And now you can start anywhere and you will just bounce around. You'll try to hit that fixed point, but you won't ever reach it because it's unstable. You just sort of cycle back and forth in a 2-cycle. Okay? And that, I think, can go some way towards explaining the on-off behavior that KIC 1255 sometimes exhibits. Most of the time it's chaotic. But the on-off behavior we can reproduce when this equilibrium bifurcates into a 2-cycle. How can we get the chaos? Well, here is where we have to think, I think, more carefully about the composition of this dust. I'm almost done. I think I just have 2 more slides to go. The point is that the kinds of grains that you condense, the gamma opacity ratio that prevails under clear sky conditions is different from the gamma that prevails, the kinds of dust grains that condense under cloudy conditions. Under clear sky conditions, gamma has to be less than 1, right? Because if gamma were greater than 1, if you absorb more strongly in the visible, you have clear skies, the sun is beating down at you, the star is beating down at you, you'll be heated to a temperature which is above vaporization. You'll never condense in the first place. So the only kinds of minerals that can condense under clear sky conditions have to be transparent. And I brought a little sample, right, just to cement it in your minds. Quartz is transparent in the visible, but glows like mad in the infrared, right? So its gamma is less than 1. Under cloudy conditions, it's just the reverse. Now, the iron vapor that's in the atmosphere is free to condense. The star is not beating down on you. So now you can form the usual kinds of silicates, right? The usual kinds of silicates have some iron in it. Things like olivine or peridot, okay, which are opaque in the visible, but transparent in the infrared if the grain is small enough. And these grains are small enough. They're submicron in size, small enough to be carried off in the wind in the tail. Okay, so now, okay, you've closed the feedback loop. Gamma is now a function of tau, and it can flip between less than 1 and greater than 1. You can sample both the greenhouse solution and also the nuclear winter solution, depends on the tau. And so now when you fold this loop into the map, now the map looks like this. It's no longer monatomic. It kind of looks like the logistic map. It's parabolic. And again, it doesn't really matter what initial condition you choose. The thing goes nuts. And you can calculate a Lyapunov time, which is several orbits. So this, I think, goes some way towards understanding the chaos that's seen for this particular object. Here's the orbit diagram. That bifurcation bifurcates infinitely, okay, into a sea of chaos. And it's our first, I think, attempt at really trying to understand time behavior for these atmospheres in a simple way. It reminds me of Robert Frost, who asked, will the world end in ice or fire, nuclear winter, or greenhouse disaster? Pick your poison. Well, Kick 1255 picks both. And it can't change, it changes his mind actually every few days. And I think this is our fate as well. Physically, when the sun goes red giant, and not only the oceans, but also the continents will vaporize, okay? It might also be our fate politically, at least in the US, where I'm observing an infinite series of bifurcations and dissolving into a sea of chaos. So I think on that note, I think I'll close this talk. Thank you very much.